One. Assalamualaikum warahmatullahi wabarakatuh. Good evening, everyone. Before we like to begin our presentation, we'd like to say thank you for the hospitality and the kindness that the audience have been given to us. We are from the Nexus 3 OmniWheel robot project-based learning team. We will be presenting our midterm progress. And without further ado, let's just begin the presentation. Okay, so the first is what is the Nexus Omni three-wheeled robot? So basically, the Nexus Omni Wheel robot is a mobile robot that uses special wheels called Omni Wheels to move in all directions, unlike conventional robots, which can only move forward or backward and must first rotate to turn. This robot can move freely forward, backward, sideways, diagonally, and even rotate in place. This is possible thanks to its unique wheel design and a control system that uses inverse kinematics. So here we are have the team members of the project itself consists of me, Dimas Rizaldi as the team leader, and Muhammad Afif Athallah as the programmer, and Muhammad Kirom Malifia as programmer, Valentino Rossi as programmer, Aidan Pradella as the mechanical team, Rayhan Ahmad as the electrical team, Nia Febrianty as the programming team, and Nurul Aisyah as the um, electrical team, and Nanik Purwaningrum as the program team. So when we do this project on this term, we face some constraints, and with some of the constraints are internal storage issue regarding the Jetson Nano, such as overcapacity, eMMC storage, and software issues. So the solution that has been implemented for these constraints or these problems is refreshing and reinstalling the Jetson Nano using Balena Etcher and other methods, and the usage of an external micro SD card to resolve the storage issues. And second constraints that we face is due to budget cuts, the intrareal sense depth camera didn't get any approval from the state. So the solutions that we already implemented is changing the proposed camera to a webcam for substitute, and it still delivers object detection for the robot. And the third constraint is the Omni robot was unable to properly receive and display LiDAR data in RFIS, which hindered autonomous navigation. So the solutions that have been implemented are reconfigured the LiDAR topic and TF frame and message type in ROS for proper data visualization in RFIS. So this is the concept design review for the robot. So basically, this robot uses Omni wheels from Nexus Robots and is designed for holonomic movements. It means that this robot can move in any direction without having to change orientation. So the specification for the robot itself consists of the wheels. Three Omni wheels from the Nexus robot are equipped with perpendicular rollers, allowing the robot to move sideways. And the motor, each wheel is driven by a motor, DC, brushless, or stepper, mounted 120-degree apart. The framework of the robot itself is made of aluminum or acrylic, circular or triangular in shape to accommodate all the components. And the control system for the robot itself, we use converting the input velocity to wheel velocity using inverse kinematics and usually run on ROS, Arduino, or STM32 with an additional control system added using a proportional, integral, and derivative, or PID for short. So for this part will be explained by my friend Aidan from the mechanical team. Go ahead.
Okay, let me introduce myself. Aidan. My name is Aidan, and I am a mechanical designer in this team. And this is our concept design of the first of the robot. We have of the up from the up we have a lidar, and the second place is we have motor driver, camera, step down, and motor and PCB. And the third, we have Jetson Nano put in, and the base of the robot we have encoder, wheels, and plat. Okay, the next. Right. Okay, primary design. This we have our object. designed to build the robot can move freely to any direction. It's like forward, backward, sideward, and rotation with using three omni wheels. Then system of review. We have three omni wheels arranged to distance of 100 direct from its another is a form a triangle. We have a size wheels is like 100 millimeter and the roller on the side of the robot and can slide. And we have motor in using an encoder it's BDAC and BLDC. Then the structure is we have circular hexagon. Okay, next member. Okay, we have in this robot we have some materials items. It's like Arduino Mega, Jetson Nano, LiDAR, motor driver in encoder and Omni wheels, battery and PCB board and step down and the last Intel cells of the camera. Okay, this is of the side and front of the view of the part of the up top is we have a LiDAR and like concept design is like same and this is will be a grow up design is not the really finished but it will be up and upgrade. Okay, for next and this is isometric view. Okay. Okay, next. And we have output get some external fan from the new component from the Jetson Nano.
Okay, this is our wiring for the robot. In this picture, we can show we use two motor because in the first driver including two motor and the second driver is including one motor. There are three DC motor connected to the driver. Each motor each motor use two wires connected to the output terminal of the L298N driver. The polarity of the connection determines the rotation direction of the motor. These motors are used for the omnibus movement system. For distribution, the main power source is a 12 lipo battery. The battery supplies power to both L298N motor drivers and the step-down converter. The positive wire from the battery is connected to the VCC terminal, while the negative wire is connected to GND. For the step-down converter wiring, the step-down converter is used to reduce the voltage from 12 volt to 5 volt. This is important because Arduino Mega requires a lower voltage supply. The input side of this step-down converter is connected to the battery, and the output side is connected to the Arduino power input. Next, and this is the wiring for Jetson Nano, including external 5 volt DC fan to the camera and LiDAR. Next.
Okay, guys, the wiring for the search data encoder. In this wiring process, all GND pins connect with GND Arduino. Because the ground connection were combined so that all components share the same voltage reference, allow the microcontroller to properly read the encoder signals.
Okay, so this right here is the robot system flowchart. So it consists of several decisions here. So first is we need to initialize the robot parameters, including the motor encoders, wheels, and the position. And then we initialize the nuts on the Jetson Nano. And it include the publish and subscribe through the through some several topics like command velocity and etc. And then we initialize the LiDAR for object detection and mapping. This consists of the robot vision itself or the camera. And then the robot will read the desired speed because it uses the inverse kinematic. And we already use the inverse kinematic uses three parameters like Vx, Vy, and speed corner. And then um, in this part, we use the inverse kinematic to determine whether the robot will be moving or no. Like for example, if the robot didn't know where the robot will be moving, it will be going back to reading the desired speed. But if the robot if the decision is yes, then the robot will be moving straight, left, spin, right, backward. And the second decision is to determine whether the speed is valid or no. So if the speed isn't valid, it will be going back to determining where the robot will be moving. And if the robot of or the speed of the robot is valid, then the robot will send command to three wheels.
This is the left picture. This is the program in Arduino IDE for the data encoder, and the right is put in serial monitor Arduino IDE. Next.
Okay, this is a program design about leader precision using AirFice. In AirFice, the RP leader A2MA was successful connect to ROS2 and display real-time data in the form of lines. Next. Next one. Okay, this is a leader result. The obstacle detection program success process scan data from the scan topic in to object in front of the sensor. When object was detected, the system displayed the status safe, while the message obstacle detect were automatic when an object with certain distance. Okay.
This is the recording of RP leader while scanning around the map by using Pbl-Room. Next. This is a recording of airplay of slam mapping by scanning around the Pbl-Re-061 map. This is a demonstration. Next. This is a gazebo simulation room by using simple maze room. Next.
This is a test result using hard cascade. This is a basic detection program before using the YOLO algorithm, which use deep learning. Hard cascade works using a machine learning approach by detecting face orientation. Some faces that are not included set will be detected by system. You can see there. This method has both advantage and disadvantage. It has an technique and good for simple detection. However, it is not always accurate and can have trouble detection fast that look different from the dataset it was trained on. So I use her cascade as an early step to build a system that can recognize the object before later developing it to be more accurate and real time.
Okay, so this is the object detection using the YOLO V4 tiny model. So the reason why we use this specific model for this robot is because due to the storage problem that has been addressed on the constraints, and despite the robot, despite this model is not that great compared to other models such as YOLO V5 or even YOLO V8, it still detect multiple objects or the classes. So as you can see here, the model detects some of the classes and it displays the frame rate per second and the inference or the delay time for the detection. And then this is the program for the object detection. It uses Coco.names datasets, and it uses YOLO for tiny config and YOLO for tiny weights. And with and without running without TensorRT or TensorFlow, the result of the object detection will be slightly deprecated than using TensorRT or TensorFlow. So here are the results of the object detection using the YOLO V4 tiny model. So the first thing is the high inference time results in low FPS or low frame rate per second. And then the model is able to detect objects or classes with decent accuracy depending on the confidence threshold used. And without TensorRT or GPU acceleration, the model tends to lag and cannot perform real-time detection efficiently due to low FPS. Average detection performance achieve around 2 until 3 FPS maximum on the Jetson Nano using OpenCVD and N. So basically, this model cannot run without GPU acceleration. So that's why we use YOLO V4 tiny model.
Okay.
Here I will explain my desk. Desk is an injection program section. So here I have tried to simulate using the gazebo and Jetson, but I could not continue for several weeks because there was a problem with our Jetson. Where our Jetson had a problem, Jetson didn't want to boot or was stuck on a black screen, so I look for a way to Jetson to boot as usual. And earlier I just tried again from the beginning for my next progress. And this is the progress that I have to do to simulate from for the gazebo. Thank you.
Okay, apologize for the delay. So right here, this is the monitoring through web application. So basically, this robot will be using web application for monitoring purposes. And this robot, and sorry, this web application uses HTML and CSS for the front end, and for the functionality, it uses JavaScript, and for the back end, this website uses PHP, and will be using localhost or XAMPP for hosting purposes. So as you can see here, this website, it consists of several pages, and it consists of the specification for the robot and the control system. And the control system that we use for this robot are PID and inverse kinematics, and the add-ons, it include the members of the project itself. So this is the project timeline. So it consists of the first week until the seventh week, and it starts off with kickoff or maybe an introduction to the project, and then the second week we plan and coordinate for the project and with our project manager, and the third week we do literature review and data sheet research to some components, and the fourth week hardware setup and the initial system development, and the fifth week, we use sensor testing and algorithm implementation, such as YOLO and other algorithm. And the sixth week, we calibrate all of the systems and we do real-time testing. And the seventh week, we integrate all of the systems and did the final testing. So the final target for this project are robot components such as cameras, LiDAR, ROS, and Jetson are already functioning properly and can be used according to their roles in the system. And the second is the robot has successfully performed localization and mapping object detection using datasets and can move autonomously. And the third is the learning module for the robot has been completed and is ready for students to use for learning. So I think that's all for the project presentation for this term. And we'd like to say thank you for the attention, and we would like to say sorry for any inconveniences. And without further ado, we will be ending this presentation with good evening. Assalamualaikum warahmatullahi wabarakatuh.